Okay, today we're going to have a look at the atomic theory section of the GCSE physics syllabus. So I'm hoping we're all quite happy with this theory of the atom. So this is the modern GCSE accepted theory that we have an atom which is made up of protons, neutrons and electrons. The protons and neutrons make up the nucleus, giving the nucleus a positive charge. Then going around the nucleus we have electrons which have a negative charge, which are found in shells, or we can call them orbits, or we can call them energies. Okay, so how did we get to this theory? Okay, as part of your GCSE syllabus, you need to know about two gentlemen. Okay, so first one is a guy called Thomson. He was around in the 1800s, late 1800s. He was from Manchester originally, a pretty special individual. At the age of 14, he was accepted into Owen College, which today is part of Manchester University. And from there, he went to Trinity College in Cambridge. After completing his master's at Trinity College, he later became a professor of physics at the Cavendish Institute. And the Cavendish Institute was a really famous institute. Many of the scientists who worked on the Manhattan Project during the Second World War, and many of the leading men associated with nuclear physics and the understanding of radioactivity worked in the Cavendish Institute in Cambridge. Okay, so Thomson put forward a model called the plum pudding. Okay, he had found electrons. Okay, so he is the person who identified that atoms have electrons, and this was his model, that your atom was mainly this positive charge here, and dotted through this dense positive charge were our negatively charged electrons. So they looked like raisins or plums in a steamed pudding. Okay, so overall then, our positively charged atom with its scattering of negative electrons throughout had a neutral charge. This model lasted for quite a while until a student, okay, from Thomson's lab came up with his own experiment in his own lab. So this is Ernest Rutherford. He was from New Zealand. So he worked in Thomson's laboratory and got his PhD. He then, as his career took off, he also became the head of the Cavendish Institute. So when Thomson retired, Ernest Rutherford took over as the head of the Cavendish Institute. And he asked his postdocs to run an experiment. Okay, and this is what he asked them to do. Okay, so he asked them to fire alpha particles. Now, alpha particles, which we're going to learn about later, are just the nuclei of a helium atom. Okay, so it's just the protons and neutrons of a helium atom. At the time, they didn't know that there were protons and neutrons because neutrons hadn't been found. Okay, another pupil in Ernest Rutherford's laboratory found the neutrons, but Ernest Rutherford had found the protons. So they had got just alpha particles, so the nuclei from helium atoms, and they fired these at gold atoms. Okay. Now, if the plum pudding model was correct, and it was an atom was this dense positive charge with negative charge throughout, firing the alpha particles at it would mean that they would all bounce off. But this wasn't what they found. They found that most alpha particles went straight through the gold atoms. Okay? Those that went near the nuclei bounced off, which is what we would expect. And those that went close to the nuclei came off at an angle. Okay? So they were like refracted. And then those that didn't go anywhere near the nuclei went straight through. Okay, the plum pudding model could not explain this. So Ernest Rutherford then suggested that most of an atom is empty space, okay, with a tiny positively charged nucleus, okay, and then that was his theory he put forward, okay. So the gold scattering experiment was how he did this. Now this is commonplace, that someone puts forward a model, it stands, and they've got experimental evidence to back it up. Then as technological developments occur, different people look at things from different angles, okay, they then come up with an experiment which disproves an earlier model and puts forward a new model, okay, and this is how models then develop. So then we'll go back to what we now know, okay. So we now know that we've got the protons. So Ernest Rutherford was one of the gentlemen who did his founding work on protons, okay. We've got electrons, which J.J. Thomson found, okay, and then a student in Ernest Rutherford's lab found the neutrons, okay, and put them all together, we've got this dense, small nucleus made up of protons and neutrons with the electrons travelling around it. Our protons have a mass of 1, and protons being P are positively charged, P for positive, P for proton. The neutrons, I've got a mass of 1. Neutrons are neutral, so they have no charge. So all the mass of an atom is held in the nucleus. And the electrons then have a very, very tiny mass, negligible mass. They don't contribute much at all, if anything, to the mass of the atom. The electrons are negative. Okay, so I'm hoping this is just a recap of GCSE chemistry. The atomic number then is a number of protons, and if we look at the top here, I've got 2 positive protons. Okay, so my atomic number would be 2. The atomic mass is the number of protons plus the number of neutrons. So all the mass is everything that happens to be in the nucleus of the atom. And 2 plus 2 makes 4. Okay, so 2 plus 2 makes 4, making this a helium atom. I've got 2 protons and 2 electrons, showing that my atom is neutral in charge. I've got the same number of positive and negative charges. Okay, so if we then have a look at some other elements of the periodic table, hoping this again doesn't come as much of a surprise. So hydrogen, H, has an atomic number of 1, so it's got 1 proton. It doesn't have any neutrons, and it has an atomic mass of 1. Helium, He, which we just looked at, has an atomic mass of 2, meaning it's got 2 protons. It also happens to have 2 neutrons, and if I do 2 plus 2, I get 4, which is what its atomic mass is. If we look at lithium, the third member of the periodic table, it has an atomic number of 3, meaning it's got 3 protons. It also happens to have 4 neutrons. 3 plus 4 makes 7, so that's its atomic mass. If we go to the 5th element of the periodic table, we get to boron, B. It's got 5 protons, which is why it's got an atomic number of 5. Happens to have 6 neutrons, so I do 5 plus 6, its mass is 11. Oxygen, 8th number on the periodic table, it's atomic mass of 16, because it has 8 protons and 8 neutrons. Sodium, Na, atomic number of 11, meaning it's got 11 protons. It also happens to have 12 neutrons, and this should add up to 23. So that is a mistake on my behalf. I should learn to check these. 23. Calcium is atomic number of 20, so it's got 20 protons. It also happens to have 20 neutrons, so if we add the 2 together, we get 40. Okay. So, again, I'm hoping this isn't something new. This is isotopes. Now, isotopes are really quite important when it comes to radioactivity, and we'll get onto this later on. But you may have noticed when you stare at your periodic table that when you're looking at the atomic mass, the numbers aren't quite round. They might be point something or other at the end. And this is because there isn't just one type or one version of a particular atom. There are numerous versions of a particular atom, okay, and these are called isotopes. So on the periodic table, chlorine, okay, has chlorine 35.5, okay, as its atomic mass. Now, there are two stable chlorine isotopes. There's lots of other chlorine isotopes, but the two major ones are chlorine 35 and chlorine 37, okay? They both have 17 protons. So if we saw them on the periodic table, they both have a 17 at the bottom, okay? Their smaller number would both be 17. However, one of them has got 18 neutrons. So if we do 35, the top number, take away the bottom number, we can see it's got 18. And the other one has got 20 neutrons. So if we do 37, take away the atomic number, which is 17, we end up with 20. They've both got the same number of protons, but they happen to have a completely different number of neutrons. Now, the same number of protons means they're the same element, but the different number of neutrons means that they are an isotope of the same element. And this is really, really important. In exams, they often ask you about what is an isotope, and they literally, for 2 marks, want you to say it's the same number of protons, but a different number of neutrons, okay? So that is isotopes. So let's think about electrons, okay? So we know that they were identified by J.J. Thomson, okay, back in the late 1800s. Then a guy called Niels Bohr, okay, suggested that the electrons then go around the nucleus in orbits or shells. So he found them, then he identified that they go around the nucleus in these orbits or shells. Okay. So if we have a look at oxygen here, this time my numbers are the other way around. The smaller number, okay, tells me how many protons I've got. So I've got 8 protons. Now, because we're looking at an atom of oxygen, if I've got 8 protons, I've got to have 8 electrons, because when I talk about atoms, the number of positives and the number of negatives has to be the same to make them neutral. Okay? I'm hoping then you'll remember in chemistry that there's a rule for how we put the electrons around the nucleus. Okay? So the rule is that 2 can fill in the first circles, okay, or shells, then up to 8 in the next shell, up to 8 in the shell after, and then we go 2 in the one after, because you need to know for chemistry the electron orbits up to calcium on the periodic table. So here I've got oxygen. I filled in the first one with 2, and I'm showing my electrons with crosses. You could show them with dots as well if you wanted to. And then I've put in 6 in my next orbit, and if I add them all up, 1, 2, 3, 4, 5, 6, 7, 8, we add up my 8. So my electron configuration is 2, 6, okay? Now, we can use this to tell me something else. So oxygen then is in row 2 of the periodic table, and rows go across the periodic table, and group 6, so it's a 6th group of the periodic table, okay? So we would go down 2 across 6, and we would find oxygen on the periodic table, okay? So we've got 2 different shells, and each shell happens to have a different energy level. You just need to know that. And the last little bit we're going to have a look at today is something called ionisation. Something you have covered in chemistry. It probably wouldn't have been described to you as ionisation, but maybe the formation of ions, the idea that metals form positive ions and non-metals form negative ions, and ionic bonding. Okay, but for chemistry, for physics, we just need to know that sometimes our atoms, so this atom here, can gain so much energy that we can cause our electrons to jump. Now, if they just jump up to the next, so if these electrons here were to jump up to the next orbit and then drop back down, they would give off some energy, and often they give this energy off as light. Okay, but sometimes they gain so much energy that they might jump out of the atom entirely. And when they jump out of the atom entirely, they become charged. Okay, so here we're giving my oxygen lots and lots of energy. An electron is going to jump out, and because I've lost a negatively charged subatomic particle, my electron, I then end up with a positively charged oxygen atom. Okay, so oxygen ion, sorry. If it's positively charged, it can't be an atom. We show that, as you do in chemistry, by putting it in square brackets. Okay, so my oxygen ion then still has 8 protons and 8 neutrons, but now it has 7 electrons. So it's got 1 less electron than it does have protons. Okay, so it's got 8 positive particles and 7 negative particles, which means if I do 8 minus 7, I end up with 1 positive charge on the outside. So this is ionization, when we cause the electron to just jump out of the atom entirely and my atom becomes an ion. Right. I hope that is really, really useful for you. Okay, feel free to just be reading through the sheets and not listening to me, but I hope this will help you.